We are now coming to one of the things that is at the core and the heart of ENAM, and that is, of course, presenting you great startups from the field of future of computing. For the startups, just some house rules. There's a clock here. You have 5 minutes for the pitches. We won't have Q&A. We can have Q&A after the pitches outside when we enjoy a drink or two. Now, we see a blank slide, and that means it's up on stage. Michael from Architectonics.
High-performance electronics has a huge problem. The cutting-edge nodes that actually make the electronics that go into your high-performance computer, that go into your laptop, are not European technologies. They are from South Korea, they are from Taiwan, they are from the US. In Europe, we don't have these kinds of technologies. Furthermore, high-performance electronics has another huge problem, that it's stagnating. We had the end of Dennard scaling, which meant that shrinking down the transistor doesn't really make it more efficient. We had the end of Amdahl's law, that adding more transistors doesn't make it more efficient. And now we're facing the end of Moore's law. And I'm not talking about making them smaller, I'm talking about Moore's second law, which means that making them smaller makes them more expensive. We at Architectonics, we believe electronics, that's not the way forward. The way forward is optical computing. The idea to use photons instead of electrons to do high-performance computation, and that's what we do at Architectonics, creating the world's first all-optical computer. And how we do that is by simply using the properties of optics to improve what electronics can't really do well. One is to parallelize. Parallelizing electronics means more transistors. In photonics, it means more colors, more wavelengths. Electronics is super slow because of capacitance effects. Photonics doesn't have that. You're basically always computing at light speed. Electronics has immense resistances, which produce a lot of heat, uses a lot of electricity. Photonics is almost like a superconductor. We base our technology on these 3 pillars. We have the software to design the chips. We have the software that runs on the chips. We, of course, have the hardware, which means the processors, the optical transistors. And we know how to do the architecture, which is not your classical von Neumann architecture. It's more advanced than that. And at Architectonics, we are able to combine all these 3 pillars to create the world's first optical computer. And our product line will look something like this. So on the one hand, we will have our high-performance processors that you will be able to buy and put into your data center for high-performance computing. And we also want to make our design platform accessible so that you could create an all-optical ASIC, an all-optical CPU for your specific need, that an Intel, once it sees the light, will be able to use our technology and do their all-optical approach as well. And what does this future look like? The main metric is how much performance you can get out of your processor by how much energy you put in. And we use here the tera operations per second per watt metric. And as you can see, our projected performance is at least 100 times higher than the most cutting-edge devices you can buy from NVIDIA at this point. And our way forward is simple. Next year, we will be presenting the world's first all-optical CPU, a device that can do general-purpose compute, but all-optical. Moving forward from that, we will start with our first deployments, moving to the end to our all-optical XPU platform that can do general-purpose compute at the performances that I showed you earlier. And we can do that because we have this highly interdisciplinary team. So I'm more the architecture, the software guy, moving top-down, whereas my co-founder, Leonardo here, he's the hardware guy, he's the photonics guy, moving bottom-up. And by combining these 2 approaches, we are able to fully integrate an all-optical computing platform. And I mentioned the cutting-edge nodes. the coolest thing about our technology is that we can do it in Europe, that we can use European nodes, that we can use older fabrication nodes, and that all our supply chain is completely European-based. And I hope I'm able to convince you that an all-optical computer and the future for all-optical computing is a European future. Thank you very much.
Okay, thank you very much, Michael. Next one up is Sven from Annabrid.
Thank you. So thank you for having us here at INAM. And I have a provocative thesis. It's the question, or it's a claim that we can do future computing without new materials. We just need a new paradigm. And, well, thank you. So we basically do quantum without quantum. So if you think how computing is done today, it's basically how you learn it in primary school, like arithmetics, computing digit by digit. And what we are doing is called analog computing, and it's actually, the name comes from analog processes in nature. So it's more like measuring things. If you sum two numbers, like these two rivers, you just measure how one water flows through the river, and that's it. You don't have to do anything else. So you basically let the nature compute for you. And interestingly, this happens in real time and doesn't use any algorithm, and you also don't need any clock. And clocks, as we just learned, are a thing which really limits us in doing progress. And it also has a property of being very similar to quantum computing. So you really prepare an initial state and measure things afterwards. But it's not quantum because you don't have a quantum state. You can really measure everything in between if you want. And you don't need all the setup you need for a quantum computer. And as I said, you don't need material research. And we call this basically resetting Moore's law because we can, as the talk we had before, we can do everything in Europe. We have big node sizes, and we don't have these requirements for materials and all the thing. And just to say why this is so interesting, because we build computers more like the human brain. So if you take AI as the use case or the business case which everybody likes, then you really see that how AI is done today is not how the brain is working. And the right is a typical picture of how brainwaves are measured with EEGs. And interestingly, you can build computers with very simple mathematical models, basically coupled oscillators, and really get a lot of strength with even less nodes than in this network. So it's really a prospective technology which can make a huge difference in NI. And what is interesting is that we are already selling computers. They don't look yet already like a chip. They are discrete, where they basically prototypes, and we sold more than 1,000 of them last year. But we made extrapolations, really conservative extrapolations from these prototype computers towards the chip. And we get incredible, well, it sounds too good to be true, basically. So it's like 1,000 times faster, and at the same time, 10,000 times less energy demanding. And of course, then means less cooling and everything. You can pack your technology much denser. And it's also interesting for electronics applications due to the little latency you have with analog processing. It's not hackable in the same way as a quantum computer is not. So really doing the comparison with quantum computing is that with our technology, we have a maturity. The technology is really well known since decades. We just bring it to the future by integrating in our chip. And it's very portable. It doesn't have to remain in the data center. It really can be embedded virtually everywhere. It can go to space. It can go into your body. It can go everywhere. It scales very well. And it's very affordable due to the big node sizes, for instance, and very manageable. To get to our key unique selling point is that AI, for us, it's only one application. We can do so much more than AI. And basically, our technology is compatible with CMOS, so it can be embedded in every existing digital processor. And it's really, we call it general purpose programming because we can map basically any nonlinear process on this technology we have. And this graph here shows you, for instance, this plane here shows you just an example that we can even steer planes with the help of analog computers in a way that these planes save a lot of energy, but also the computation is faster and actually not in this way not manageable with digital electronics. And we have the vision to bring this technology really into every processor in the world to foster what we call hybrid computing, analog and digital going together. And just to give you a glimpse on the team, so we have a set of 4 founders. We have now 15 people in our team. We have made a Series A, now it's seed round basically this year. We have, but also existing revenue, so we are revenue-based. Before this seed round, we are even bootstrapped. We have customers because we are already selling, and we have created a number of programs and are in a number of running programs by public agencies and privates. So thank you for your attention, and I give over to the next one.
Thank you very much. And next one is Mitun from Nanomatter.
Hi, we are Nanomatter. We are an advanced semiconductor manufacturing company. We make materials by which we can make 1 trillion transistors possible on a chip. So the evolution of computer technology depends upon increasing the number of transistors by reducing the size of transistors. We were able to do this with silicon, but silicon has reached its physical limits, and we need new materials. And we have the new material that is TMD, so transition metal dichalcogenides. We can make these materials using metal organic chemical vapor deposition equipments. So the big industries such as TSMC, Intel, or Samsung has announced that they are going to launch TMD-based chips by 2030. And the biggest regulatory bodies like European Union has come with EU Chip Act, which explicitly tells the importance of 2D material as next generation of advanced semiconductor material for chips. So there's a compelling need right now in Europe for having this technology developed here. So what are these materials, TMD? They are transition metal dichalcogenides. They are atomic plate of materials with transition atoms with 2 planes of chalcogenide atoms sandwiched between 1 layer of transition metal atom. They have a crystalline structure like that. And due to its crystalline nature and 2-dimensional character, we can make 1 trillion transistors possible on a chip. They are energy efficient, and they have direct and indirect band gaps, and they can be used for photonics and electronic applications. So at the moment, for adopting this material industry, there are a couple of challenges. The biggest challenge is for having TMD-based chips, we need high quality, large area, thin film wafers needed for fabricating devices, which is not possible, which is not available in the industry right now. And this industry needs a lot of R&D, and the cost of ownership equipment is so high that the R&D cannot adopt or do the research for these materials. And EU Act explicitly said that around 400,000 skilled labor is needed. At the moment, this is also not available. So at the moment, what we can make is the discontinuous thin films like that, what you see in the optical image as well as in the scheme. What Nanomatter can do is Nanomatter can make continuous high-quality films on which we can fabricate devices. We decrease the cost of ownership by 80%, and by that there will be a lot of, by making an affordable solution, there will be large-scale adoption by which we can solve the problem of lack of trained skilled labor. We have applications in photonics, electronics, and optoelectronics. We make MOCVD equipments. We need large-scale production, and we can do technology integration by making devices based on these products. So that's our flagship product, which is a CVD system with the inbuilt characterization tools. We have developed this in our university as a part of our academic research. Now we want to come to the market and sell this equipment for industrial and academic research as well as small scale and large scale production. So we can also make devices such as TMD-based transistors, TMD-based photodetectors. We can also make sensors and optical coatings. You can come to our booth. We can talk more about the specifications of these devices. We have been continuously talking with our customers. We are now working with 2 foundries. We are working with 3 companies, and we got LOIs or MOUs with almost 35 research institutes. So our team is expert in this. Myself, all of us have a PhD in either nanotechnology or physics. Myself has a management background as well. Professor Anthony George, he has been working in this area for the last 12 years, and he has almost come up with 80 publications on this material. And we also have 5 patents, which is based on the devices developed using the equipments that we made. Imad, he done his PhD on TMD-based materials and devices, and Nuis has a PhD in making optical setups. So we want to accelerate the adoption of TMD materials to the market. So if you're developing any product which you think has a TMD element in it or process, or if you want a customized MOCVD equipment, you can please come to us. We are here for collaboration. Thank you.
Thank you so much. And now we have the next startup with an N, NextGo EPI, up on stage, Tanshun.
Hello. Yeah. Hello. Thank you, Oliver. So, hello, everyone. So, before I start, I want to ask you all about one question. Have you ever used ChatGPT? I think the answer will be yes. And how many times do you use per day with the ChatGPT? For me, let's say, so this is a number I want to tell you. So 6 queries in ChatGPT-4 will require the energy needs for 1 LED light with 60 watts for 1 hour. So if I want to write an email to my German landlord, I can easily use all the electricity we need today to light this building. And I also need to add one more query, is that please translate everything in German. So I will use more energy than most people up here today. So this is the fact we have to use the future computing tool. Yeah, and there's a report already mentioned that maybe by year 2027, the power or the energy needs to support all AI service is equivalent to a small country, for example, Belgium or the Netherlands. It's actually a very power-intensive tool to use future computing. And there are many more, not just ChatGPT. We have Google, search, database, semiconductor manufacturer, Bitcoin, electric car, and VR, metaverse. Everything, all service needs computing, and all service need electricity. And how efficient we are as a human being to use electricity is very bad. In Germany, in 2021, 65% of energy is lost only in 1 year, based on one report from the government. So basically, the bill you pay every month for your electricity, actually you pay for the energy you never use. So if a people is poor and want to make money or want to overcome the financial issue, there are 2 ways: make more money or save more money. And today, we are going to tell you the second way, how to save money. So to save your money, our company is going to deliver this new semiconductor gallium oxide epi wafer to the market. This is a material used in the semiconductor chips. Imagine a chips is actually a toast, a delicious toast, and epi wafer is actually the gems on the toast, and we are one of the best gems maker. And if you Google what is gallium oxide epi wafer, this is a buzzword you may get: wide bandgap, power electronics, silicon carbide, something like that. But today, I'm going to translate to human language for all of you. So, why gallium oxide and what is gallium oxide? It is a semiconductor material which has a wider bandgap compared with the current used semiconductor, and it also has wide beamformed figure. What's that? Let me translate it. Which means that this material can support even higher voltage compared with all the compound semiconductor used in the current society, and it will have less power loss when you're operating the device. It is a more efficient choice. Second, it's also most cost-effective. I don't want to call it cheap, because we are able to grow this material using the technology we use to grow silicon. So it's a much cheaper way to produce such material. If you compare with the silicon carbide, the hottest material we are using now, the cost is only 1/3, or it can even lower compared with the current technology we are using. And it has a fast development path. So compared with silicon carbide, it takes 30 years to go to 8-inch. But for our material, in less 15 years, we are already achieved the same scales of the silicon carbide. It takes 30 years. So it will be fast on the market, and it's not just a dream. And as a company, we are already developing this market. It's not just a proof of concept. It's not a MVP. It is a product which is delivered to this industry, automotive, power electronics, renewable energy. Those companies, they will come to us and buy our material for their device. And we already have some early customer in the United States, in Germany, and some potential customer in Japan and Taiwan. They would like to buy our material for their device. And this is the market of the gallium oxide. So in the right-hand side, you can see the total market of the power electronics can up to 50 billion. And also there are some other applications. Just looking at the automotive market, by year 2030, the market will reach 2 billion, even you only consider 20% of the market penetration of our materials. So, as last sentence, I want to let you know is that, as Henry Ford said, if I ask people what they want, they always want a fast horse. So our mission, the mission of our company, is want to tell the customer in the market that forget your old horse. We have the Ferrari here. We have a faster choice. Please come to us, and we want to deliver the material to satisfy the needs to development the next generation power electronics. So we are Nesco happy. Future computing is our future, and we power your next century. We power your future. So we have the booth outside. We also bring our product. Please come to us. We can share more information with you. And this is our excellent founding teams. We have 10+ year experiences, many amount of publication, and 2 international patents for our process and product. Thank you so much. Yeah.
Thank you, Tashun. Okay, next one up is quantum grade materials from not Berlin but Brandenburg, right? Oops, no, sorry. There you go.
Yeah. Hello, I'm David Übel from Quantum Grade Materials, and that's a German slide. We sent you English ones? Doesn't matter, probably? Okay. Yeah, and our mission is the production of the raw materials of the future made in Lausitz. So what is that raw material of the future? It's silane 28, a gas, silicon hydride, isotope enriched, which is currently not available on the world market, but necessary for quantum computer chips for spin-based quantum computing. I want to give one more example for the application of quantum computing, which is the search of new active compounds for medication, and in this case, Alzheimer's. The company La Roche published an algorithm for the search of such an active compound and found that it would take 1,000 years to solve that on a conventional supercomputer. With quantum computers, we could reduce this times to 1 minute. But coming back to silicon 28, as I said, it's currently not available on the world market, and we want to change that with a production based in Brandenburg, in Lausitz, and thus in the center of Europe. We are a team of a chemist, a media scientist, and a material scientist, and we need 1.7 million for the first 18 months, in which we want to build up the facilities for this chemistry startup, the majority of which goes into the facilities, the setup of the facilities, and the rest splits up mostly into personnel and the expensive chemical compounds we need. As a chemical startup, we profit from an economy of scale. You see that in the green graph. Within the first 10 kilograms we produce, we lower the cost, the end cost to our customers from 800,000 euros per kilogram to half, 400,000. And these 10 kilograms are the current world market, which will grow until 2030 up to 100 kilograms yearly. And that's the scale of our facilities we want to set up. Our end customers are now research institutes which are working on spin-based quantum computers, and in the future, CMOS producers as TSMC, IBM, Intel, and Infineon. Yeah. Thank you.
Thank you very much. Okay, now we come to our international startups. Sorry, I've skipped that. And Planck Technologies. Mariam from Norway.
Hi, everyone. We are Planck Technologies. We are empowering the energy storage solutions by designing the future of materials. Norwegian-based, we're working with optimizing materials for energy storage applications. And what we do is that we optimize the current materials and discover the next generation energy storage materials, focusing on batteries, on also chemical energy storage. We want to optimize the performance, be it like the energy density and life cycle in a battery or uptake capacity in a hydrogen storage system. So then net zero is a reality, and renewable energy like wind and solar are contributing to the net zero future. And we know that because of the inherent nature of these energy systems and being intermittent, we need energy storage to be in place. Having worked in energy industry, come from Equinor, the energy company of Norway, we have felt the problem of energy storage from close. And we, for example, had one case where we wanted to remove a generator and substitute a battery. And it was a very good business case, but we had problem with the size and with the weight of the battery to be in a FPSO. Similar problems that like we have even like the biggest battery in the world is not enough to do the peak shaving for a typical size wind farm. That's what we want to address, and what we do is that we tap into databases of materials and we do material screening based on the need, and we kind of link the chemistry to the end use requirements by translating the end use requirement in a higher scale to non-material properties. So what we offer is safe and sustainable by design materials, which offer higher value and lower carbon footprints. Trying to go to next. So we link the market to the overall predictions of the power installation in the future. And we see these numbers from McKinsey and Company. So this is kind of showing the need for stationary energy storage applications in the future. Hi. So here just going to one case study, which is on hydrogen case. For storing hydrogen, since this is a very light gas, we need to store it like even very high pressures or very low temperatures. Or there are other ways like physisorption and chemisorption. And the focus that we are having in this project is on physisorption and using metal-organic frameworks as one family of materials to do the storage. So we can kind of define some filtering for the materials, and there are more than 1 million material in the database that we're working with. And we kind of define it based on like the need, the surface area needs to be high, and we need to kind of accommodate to hydrogen, so the pore sizes should be bigger than the size of hydrogen, and so on. So these are like some of the criteria which kind of makes the optimal scenario for hydrogen storage. This is showing just the data from the CSD, from CCDC data center, around 900,000 materials which are introduced, and like 100,000 of them, there are meta-organic frameworks that we're studying. And through the filtering, we have come up with like some lower number that we need to do calculation on. So we're using a mix of computational chemistry and machine learning to do the material screening. Yeah, so as mentioned, so we kind of link the chemistry to the end use cases. What we're doing is that we kind of define a matrix of use cases, and based on those use cases, which kind of have different requirements in place, like some of them with a volume and some of them with a weights, and so on. We kind of define subcategories of materials, and we do material screening based on that. And then, like with a lower number, so we can kind of go to computational chemistry calculations and do further analysis. This is our team, combination of technical and commercial background. Hamid and Tim are the technical experts, both from the chemistry background and chemical engineering, and Kavi and Yasaman are helping with business development. We have two scientific advisors, one Professor Yangshao Horn, battery expert from MIT, and Mohammed from University of Toronto, who is an expert in the machine learning field. Yes, this is us, Planck Technologies. We're working with optimizing materials and discovering the next generation materials for energy storage applications. Happy to talk to you later.
Thanks a lot, Mariam. Thanks a lot. And now we're coming to the last startup of this set, and I need to fast forward again. And we have Quantum Motion, and Fernando back on stage here.
Thank you. I'll put my quantum motion hat on now and reemphasize some of the things that we already talked about in the session Emerging Materials. So we are here to talk about the future of quantum computing in general. And at Quantum Motion, we believe that that future will very much look like driven by silicon technology. But that future may look different. It may look quantum. And what is quantum? Well, we talk about these quantum computers use concepts of quantum mechanics, such as superposition or entanglement, to allow us to solve better problems such as factorization, that is essential in online security, database searches, that is ideal for the big data era, and for optimization problems that are applied in the financial sector and weather forecasting. And from the point of view of a physicist, quantum computers offer even more beautiful solutions for the simulation of new chemicals, new materials, new medicines. The thing is that we already touched upon this, that without hardware, there is no quantum computing. And building a sufficiently powerful quantum computer is the biggest challenge that we have out there for the field. People are trying to build these computers with superconductors, Majorana particles, neutron atoms, photonic implementations, and ion traps. But the thing is that to unlock some of the markets that will be unlocked through the solutions that we've already mentioned, that are multi-billion markets, we need affordable quantum hardware, affordable and scalable. And the solutions that we just mentioned only get us so far up to here at the discovery phase. We need a better solution. So I wanted to ask you, what do you see on screen? What do these items have in common? They have all been superseded by solutions based on silicon technology, like digital radios, CMOS cameras, microprocessors, solid-state memories. So what if we could do the same with quantum computing? What if history repeated itself, and we could build quantum computers using silicon transistor-based technology. This question is the question that quantum motion tries to answer. And that's what we do. We modify modern transistors in such a way that we can capture single electrons in the channel of some of those transistors and use the spin of that electron as our quantum computational unit, our qubit. We are a fabless company. We work with tier 1 foundries and advanced microelectronics facilities to build scalable spin qubits in silicon quantum dots, to produce low variability and high yield quantum computers, as well to achieve closer integration between the quantum hardware and the classical one. Our mission, very simple: use industrial manufacturing to enable the scale-up of silicon spin qubits and the scale-up in general of quantum computers. And I wanted to show you on screen our latest chip that we call Brixton. It contains more than 3 million transistors on a single 3x3 millimeter chip, combines digital, analog, and quantum electronics that has enabled us to rapidly characterize thousands of devices in a matter of minutes. And it allows us as well to have a platform to develop cryogenic electronics to support the needs of the quantum computing industry, our needs, and the general needs, as well as those of the space industry. This can only be achieved by a multidisciplinary team that is led by our chairman, Alberto Sangiovanni Vicentelli, that is the founder of very well-known companies such as Synopsys and Cadence, as well as quantum hardware experts, integrated circuit design experts, machine learning experts, as well as quantum algorithm developers. We are not racing right now. We've been successful with our Series B recently, raised more than 42 million from companies such as Bosch, Porsche, and Sony. And at the moment, we are the largest silicon-based quantum computing company in the world, as well as the best-funded quantum technologies companies in the UK. However, if you have interest, please come and talk to me after the presentation. Thank you very much. And let me just send a final message. Let history repeat itself. Let's have a silicon revolution again, but in this case, a quantum one. Thank you.
As we wrap it up, we have one key agenda point still to cover. Beyond that, I think we can start wrapping things up, and I'd like to ask on stage also my colleague Asa, who has been running sessions in parallel to me. Thank you very much for that, and a warm applause also for her. I think what we've learned of the day, and looking at the audience, looking at the workshop, looking at the presenters, looking at the startups, there is a need for an ecosystem that connects all the different players across verticals, across the various players, from academia to investors, from corporates to small and medium enterprises. And particularly if we look for the future or into the future of computing, such ecosystems will be of great help to push things forward and to really help us create a use case driven, purpose driven, and then at the end of the day also impact driven future, not only for computing, but also beyond. Asa, what's your takeaways from the key sessions that you had?
Great, thank you, Oliver. Maybe best is to start like chronologically, right? We had the first session that was, of course, about mostly the technical matters of quantum computing. But I think you all heard me. I said that over there already, that I really liked it, that we talked about hardware, we talked about the algorithms, and then we talked about the application, that also has to be, of course, studied. And then we moved on to the other sessions, the sessions that we had over there about the funding and regulations. We actually pinpointed the availability of the funds, which is helping the research institutes, as well as the transfer to the startups, which is important. But not only the public funding, but of course the private sector is also very important and is helping us in that direction as well. Then we moved on to the use cases. It was a very great overall overview of all of the use cases that are available there. We heard very specific sort of hardware from SAS, of course, and then we also looked at the VC side from the Lunar Ventures, and of course Ilium, who was aligned with us, and that was great too. And then last one, which was such a full of information on the talent that we didn't get to the discussion, but of course we would like to continue the discussion, was about the talent from the EIT raw materials, IBM, as well as the commercialization reactor, and a lot of interesting subjects were actually pinpointed there, what is already available to train the talent for the current need and also for the future as well. And that was what I myself have covered through the day. That was very nice. I thank all of the speakers and also all the attendees. And I guess I should pass it on to you, Oliver.
Absolutely. Thank you very much for this great summaries, Asa. That's great. And I'm dreading the sessions that I've missed. Great. Now we're coming to the last agenda point, and we had a bit of a competition. We didn't make it really publicly, but we did have a bit of competition between the startups that were pitching. And we are inaugurating, so to say, today, the Enum Future of Computing Award. And I'm super happy to give the very first award that we are handing out today with the jury, and particularly with Sabina Jeschke as a co-jury, to Michael Kistner from Architectonics. Big round of applause. Congratulations.
Congratulations.
Oh, let's do a quick picture. Is that okay?
Yeah, sure. You have to be in the middle.
In front of the table. Okay, and that more or less concludes our very first Future of Computing conference. I would like to thank, in particular, all our contributors, our speakers, our startups, and most importantly also Sabina Jeschke and Jens Eisert, who obviously had to leave because he's flying out to somewhere in the afternoon. But thanks to our keynote speakers, and last but most certainly not least to the Enum team. Asa, you know already, but there's also Chris at the back who's been helping out. There is Sylvia and Nahida over there, and Amar, you know, also. Big thank you, of course, also to our sponsors. That's the Berlin Senate, the Senatsverwaltung für Wirtschaft, Energie und Betriebe, and our exhibition participants, the startups, as well as Berlin Partner and SARS. Thank you very much for being here. Thank you very much for contributing to this, and we hope to repeat this and grow this and bring together the community that enables the future of computing across verticals and from all walks of life. Thank you very much, and now enjoy the networking.